going over physical properties. The good news is it's short. The next piece of news could be good or bad depending on how you feel, is it's pretty much just memorization. Okay, it's just, you need to know these couple of things, just have them on your fingertips for whenever a question pops up that involves physical properties. So, physical properties are properties of an organic molecule that don't need to undergo a chemical reaction to be measured. A few things they depend on include mass, branching, and intermolecular bonding. Notice I've filled in a lot of things here because I don't want to forget to talk about it. All right, it's intermolecular bonding. Okay, so boiling point. Also, I just want to say a lot of this has to do with intermolecular attractions. You're going to notice, you know, with boiling point, there's a lot of things that affect boiling point, but it all comes down to the same reasoning. Intermolecular attractions and how different physical properties affect intermolecular attractions. So remember, something we need to remember about boiling point. What is boiling point? What is it, like, what's going on? Okay, boiling point is the transition we have when we go from a liquid to a gas. Okay, so down here, this is important as well. So in order for us to turn a liquid into a gas, we need to break the intermolecular forces, keeping the molecules close to one another. So in a liquid, you know, they've got molecules and they're very close to each other, right? And they're all knocking up against each other. Because they're in such close contact, there is significant intermolecular bonding, okay? They might be dynamic, right? In a solid, it's solid, so it's not dynamic. But in a liquid, it's dynamic, but they're still there. In order for a molecule to turn into the gas phase, when molecules are in a gas, it means there's basically no intermolecular forces of attraction between them. Okay, so basically, those intermolecular forces between different molecules, we have to break them in order for them to get into the gas phase. Okay, as long as they're significant, they'll remain in the liquid phase. And so we use temperature to bring up the energy in order to break those bonds. And okay, so really what it comes down to is the stronger your intermolecular forces are, the more energy you have to put in to break those forces for them to go into the gas phase. And that means, you know, you have to put in more energy. Well, what is energy? In this case, it means heating up the molecule. Okay, we have to put in more heat to break the stronger intermolecular forces. So, if that's, you know, I mean, that's pretty much the answer to all of these, just different facets of looking at it. So, we'll start with branching, okay? So as branching increases, boiling point increases. Now this is where you get to choose. You can just memorize that if you'd like. I mean, lots of people do that. If you want to go a little bit deeper into it, you know, why is it that when branching increases, the boiling point increases? Well, my bad, I just realized I wrote that wrong. Hold on, guys. Okay, as branching increases, boiling point decreases. See, this is why I don't memorize things, because I'll, you know, you'll get it mixed up. Okay, so if molecules are not branched, so see here I have a straight chain, an unbranched chain, whereas over here this molecule has the same number of carbons, but we've got these branches coming off, okay? But when a molecule is not branched, like this one, they can have increased surface area contact with other molecules of themselves, okay? We're usually assuming we're in pure substance, pure solution, okay? So imagine this, you know, here's one of the molecules, right? But what if I took another molecule and it's floating, right? Because we're in liquid, so they're just floating around. But if you can see, even in, you know, they can kind of do this overlap, right? They can overlap each other a lot. But if we have a branched molecule, let me get rid of this. If we have a branched molecule, they still overlap, but we can't get as much surface area contact with a branched molecule. So you know, it bumps up to this one, bump, bump, bump. Really, the only way that they kind of interact is like this, or maybe it can get close like that. You see how, you know, the molecules can get close to each other, but the amount of surface area contact that we can have is not very high, versus the unbranched molecule, which can be like this, or you can have total contact like this, right? So we have a lot more interaction here when you have unbranched versus branched molecules. Okay, so if you have an increased amount of contact between these molecules, that means, and remember for hydrocarbons, the intermolecular attractions that they experience is London dispersion forces, van der Waals forces, okay? So they're very weak, but when you have many of them, when you have lots of weak little forces working together, it's kind of like Velcro, right? One little hook is easy to pull, but when you have a huge surface area and you have to pull the Velcro apart, suddenly it's not so easy, okay? All right, so as branching increases, the surface area that the molecules can have with one another decreases, which means there's less intermolecular forces, okay? Which means that they are easier to pull apart, okay? So branching increases, boiling point decreases. All right, so mass is really related to kind of like, well, it's related to surface area, okay? So let's read this. As the mass of a molecule increases, boiling point, this should be increases. Okay, so as usually as mass increases, that means that the molecule gets bigger, okay? And if the molecule gets bigger, then that means that you're probably going to have more surface area contact with other molecules, which means you're probably going to have more intermolecular forces acting on those molecules, okay? All right, and so this is kind of the trend that I have. So as mass increases, that means your molecule gets bigger, which means the surface area contact with other molecules gets bigger, which means you'll have more intermolecular bonding, more London dispersion bonding between your molecules, which means you have to work harder to pull those molecules apart to get them into the gas phase. Okay, polarity. As a molecule becomes more polar, the boiling point increases. Why is this? Well, it's the same reason, right? So as you increase the polarity of a molecule, that usually means that you're going to have stronger intermolecular attractions, okay? Stronger intermolecular bonding, okay? Doesn't necessarily mean that you'll have more, it just means that what you do have, you'll become, the intermolecular forces will become stronger. So if you look at this chart down here and the bonding, right, hydrocarbons have pretty weak attractions where they're just working with van der Waals attractions, okay? And then if you move up in dipole, you can have a molecule that just has a dipole, and so it can have dipole-dipole interactions with itself. And that is a little bit stronger than the van der Waals. Actually, it's a good amount stronger than van der Waals. Okay, and then if you look here, we have even stronger bonding when you have hydrogen bonding. And that's because, you know, when you have the components to make a hydrogen bond, those are extremely polar. So polar that they're kind of like a special thing, which is what hydrogen bonding is. And we talked about hydrogen bonding in I think the very first video, maybe the second video, one of the early videos, and we talked about the two things you need to have hydrogen bonding. You need a hydrogen bond donor and a hydrogen bond acceptor. Okay, so you'll want to remember what those were. And then lastly, with the highest intermolecular forces we have are ionic. And that is very, very polar. You just have a negative charge and a positive charge, and those inner electrostatic attractions are very strong. Okay, so that's really what I think about when I think about polarity, because pretty much as you move to the left on this chart and you have stronger attractions, stronger intermolecular forces, the reason that that is happening is because they are becoming more and more dipoled, right? More and more polar. So this molecule is going to, if it's in pure solution, it's going to be having van der Waals attractions between it and its neighbors. But this molecule, right, we have that pretty decent dipole here with a partially positive down here and a partially negative up here. That's going to be dipole-dipole interactions. All right, and bonding. So as forces between molecules get stronger, the boiling point increases. And I guess this is sort of really what we were talking. You can technically think about all of these as affecting bonding, I guess, but this is the bonding type, which I think is kind of almost the same thing as polarity. It's very similar, right? But it's the same idea. It's the same idea. Okay, now let's do one little fact about melting point. You should just memorize this. All right, so remember, melting point is different from boiling point, of course. Melting point is when we're going to transition from a solid to a liquid, or a liquid to a solid, depending on which way we're going. But typically, the way I like to think of it is solid to a liquid. Okay, well, that's the melting point. So being highly symmetrical will cause a molecule to have an increased melting point. I guess this should say a larger, I'm going to say an increased melting point. And this is because of packing, okay? So if you have a molecule that packs into a crystalline structure well, then that means it's going to want to stay in that crystalline structure and not want to go into a non-crystalline structure, like a loose structure, right? And that's what melting is. Melting's going from a solid, which is like a crystal-like structure, to a liquid, which is very fluid structure. So what happens is if you have a highly symmetrical molecule, they fit into a crystalline structure very well. A lot of times it's because they can have repeating units, and so they fit into these crystals more uniformly, right? And so they're really good at being crystals. Since they're so good at this, you have to put in more energy to finally get them out of that crystal structure and into the liquid phase, okay? So that's how I remember that. So out of these two molecules, this would have a higher melting point. This would have a lower melting point. Okay.